we have this time Andrew here to talk about some work that he's been doing on what they're calling data models. This is not exactly privacy, even though this is the privacy work sort of slot, but I think that this is actually something that's very important to understand for understanding privacy, and we have some work that trains a bunch of stuff that's very similar to what they've been doing, and actually sort of I managed to throw out like a month's worth of compute because I could use some of the infrastructure that they built and redo the thing in like a couple days. And so that was great. But yeah, I hope people find this interesting. So Andrew, yeah, please go ahead.
Thanks so much for the introduction. As Nicholas said, I'm Andrew. I'm going to be presenting our very recent paper that showed up on arXiv yesterday, Data Models, Predicting Predictions with Training Data. And this is joint work with Sam Park, Logan Engstrom, Guillaume Leclerc, and Alexander Maudry at MIT. Okay, so I want to start with basically looking at the anatomy of a machine learning prediction. So I'm going to look at a single prediction. It's this picture of a dog. I fed it to a deep neural network, and it's classified it as a dog with 85% probability. And sort of as machine learning people, we have this intuition that this prediction is a function of the training set that we used to train the model, and the algorithm that we fed this training set to. And some combination of these two factors is what resulted in the model output. But the exact sort of how these two things combined into the model output is less clear. And this is sort of evidenced by a lot of unintuitive correlations that look like they came straight out of the training data into predictions. And so the question that we want to tackle, that we wanted to at least make some progress towards, is how exactly do the training set and the learning algorithm combine to yield model output, even for like a single fixed test example like this dog. And our proposed approach to this is what we call data models, or the data modeling framework. So before I introduce the framework, I want to redraw the standard machine learning pipeline again, this time in two stages. This is how at least I typically think about the machine learning pipeline. Stage one is like the training stage. So we start with a training set, for example, like the ImageNet training set. We apply a learning algorithm to it, and the result of that learning algorithm is a fixed model, like a neural network. After we have that fixed model, we move on to the inference stage, where now I can take new test time outputs, and I can produce predictions for them. And then I can compare those predictions, for example, against like a ground truth label, or make whatever decision I want to make with it. And this pipeline kind of has a lot of really complex steps. Like the algorithm is usually thousands of steps of SGD for deep learning. The model is like a really weird neural network. Even the test examples, it's unclear where they came from. And so the point of the data modeling framework is we basically wanted to black box away all of the hard stuff about this pipeline. And what that looks like is basically, instead of having all these steps, we want a direct function from the training data to the end model output, sort of abstracting away all of this complex stuff in the middle. Okay, so to operationalize this, to make it a little more precise, I want to define something called the model output function. And the model output function, you saw it a little bit on the first slide, it's just going to be this function f that's going to take two arguments. A specific test time input, so for example, the same dog from the first slide, and a training set, S prime. And specifically, this training set should be a subset of some global training set S. So for example, the test image, the X might be like an example from the ImageNet test set, and S prime is any subset of the ImageNet training set. And what this function f is going to do is it's going to take the subset S prime, train a model on it, and then evaluate on this test input X. And by evaluate, we can evaluate can mean a whole host of things. It can be the prediction, the loss, the correctness. In our case, we looked at the correct class margin, which is like the difference between like the dog logit and the next highest logit, but it really doesn't matter. So we'll just black box it and think of this function as f. And the important thing is that f encapsulates the entire process of like training a model, SGD, evaluating it, all those steps from the previous slide. And our goal in data modeling is to for a specific target example X, so for this dog, what a data model for X does is it should approximate the function F in a way that satisfies two key properties. So what we're looking for is we're looking for this alternative function G that approximates F across a wide variety of subsets of the training set, S prime, while also being easy to analyze. So our eventual goal is to throw away this F because it has a bunch of really complex steps and instead just study G, which is hopefully like a closed form approximation of the entire process of training a model and evaluating on F. Okay, so how do we go about constructing this function G? So again, we're going to fix a specific target example X, and we're just going to think about approximating model outputs on X across a variety of subsets. And our idea here is to actually use the supervised learning framework. So given any subset of the training set, so here I have a training set of 16 fake images where 16 fake images where 5 of them are highlighted, so that's our subset. Given any such subset, I can really easily train a model on that subset and then evaluate that model on my target example X. And in doing so, I can basically collect this pair that corresponds to a subset and the result of training a model on that subset and evaluating on X. I can then choose a different subset, train a model on that subset, evaluate on X again. That's another pair. And I can do this over and over and over again. And as long as, like Nicholas said, as long as you have the infrastructure to train a whole bunch of models like this, you can basically construct this new training set where the training examples are subsets of the ImageNet training set, or in our case, the CFAR training set. And the labels are model outputs after you train on this subset and evaluate on X. Our idea then is going to be to try to fit a model from these subsets that predicts what the output of F is going to be. So we're going to try to, basically fix some parameterized model G theta to this collection of subset output pairs. Yeah, and of course, feel free to stop me at any time if I've said something that doesn't make sense. Okay, so there are two kind of remaining questions before we can really just go ahead and implement this. Question number one is, how do we generate the data? And what I mean by this is, which exact subsets of the training set should we use to generate these training examples? And the second question is, what kind of model should we fit? So I said we're going to fit a parametric model from subsets to outputs, but what does that mean? What does that model actually look like? I'm going to sidestep the first question a little bit, just because I think the answer isn't as interesting. But long story short, we're going to fix some constant alpha between 0 and 1. And then we're going to pick subsets as random subsets of the training set of that size. So I might pick alpha equals 20%. And I'm going to generate my entire training set by sampling random 20% subsets of the CFAR training set, training on them and evaluating. And the reason for this is we have some hypotheses about why different alphas would work better for different cases. But for now, we're just going to sort of skip over this question and think about the second question, which I think is a lot more interesting. So recall the second question was, what sort of model should we fit to predict the output of training on a subset and evaluating on X? And what we end up picking is a really simple linear model. So remember that our two criteria for what we wanted our approximation function to be is simple and predictive. So we kind of thought, okay, we'll figure out predictive later. Let's make sure it's simple. And so what a linear model looks like in this setting is we're going to take each subset S from a few slides ago where we had like S and then the corresponding output. And we're going to consider the indicator vector of each of these subsets. And an indicator vector for a set is just a vector whose length is the size of the original training set that has ones everywhere where we included an image, an example, and zeros everywhere else. So for example, in this global training set of 16 examples where I selected these 5 for a subset, the corresponding characteristic vector is this like 1, 0, 1 vector at the bottom. The only learned parameter here is just a linear weight that's going to be multiplied by this indicator vector to yield model predictions. So this is going to be a learned vector whose length is, again, the length of the training set, of the global training set. That's going to have one weight corresponding to each training example in like the big training set S. So this is like, essentially we tried to think of the simplest possible instantiation of this approximation function G. So the only remaining question now is how exactly do I, now that I have this parameterization, what does fitting look like? So just to, I guess, refresh everyone's memory, I brought up again the form of the training set that we have available to us. We have a bunch of subsets, Si, of the training set, along with their corresponding model outputs. So the result of training on Si, training a model on Si, and evaluating on the fixed target example X that we care about. Given this training set, we're going to solve basically a super standard linear regression problem. We're going to minimize over all possible weights. We're going to average over all of the training examples that we have. And then the inner term here is just the difference between what our function G thinks the output should be, which is this linear function, again, of the indicator vector of the subset. It's the difference between that and what the function actually was. So the result of training on Si and evaluating on X. We also added some regularization, which turns out to be important both for sparsity reasons, so making the weights afterwards easier to look at and do things with, but also for generalization. So we find we're better able to predict. We're better able to predict model outputs with some L1 regularization. Okay, so that's actually all the ingredients we need to be able to construct data models for any given target example that we care about. And so I want to put it all together in one slide and then maybe give people the opportunity to ask anything I glossed over too fast. So let's instantiate this in the context that we actually did in our paper, or one of the contexts we actually did in our paper, which is constructing data models for deep neural networks trained on the CIFAR-10 image classification dataset. Okay, so I start with this repeat 500,000 times, and this corresponds to the number of models that we trained. We're going to choose a random alpha fraction, so let's say 20% of the CIFAR-10 training set. We're going to train a model on the subset. We're going to measure the margin for every test image that we care about. So for the moment, pretend we care about only one test image, we would just measure the margin on that test image. And then for each test image that we care about, we would record both the indicator vector of the subset, as well as all of the margins from all of the test examples that we care about. Once we've collected this sort of new, what we call a data model training set of 500,000 trained models, for each test image, all that's left is to fit a linear model, as we did on the last slide, from the indicator vectors to the recorded margins. And I just want to highlight the way that we trained 500,000 CIFAR models is, as Nicholas mentioned, we recently released a library for that kind of specializes in training models really fast and in parallel. And that's what we used to get CIFAR training time down to seconds, which made all these experiments possible in days instead of months or years. Okay, so the result of this process, assuming we care about all of the test examples in CIFAR-10, is 10,000 different data models, each one a linear function that's specialized to predict model outputs for its corresponding test example. Each one of these is parameterized by a vector that lies in like R 50,000. It's a length 50,000 vector where 50,000 is the number of training images in the CIFAR dataset. Cool. So that about does it for predicting, for like constructing these data models. So at this point, we have 10,000 linear functions that we fit with standard linear regression. We ensured they're simple by making sure they're just really linear functions acting on binary vectors. Now comes the time where we have to figure out whether these are actually useful for predicting model outputs. And so to evaluate data models, what we do is sampled a bunch of new subsets. S, again, like same alpha, like 20% of the data set. I sample a bunch of new 20% sized subsets of the CFAR10 training set. I train on them, and then I'm going to, I train like a ResNet on them, and then I'm going to compare what my data model thought should happen to what actually happened in terms of the margins on all the test examples that I cared about. Okay, so I'm about to show a graph of what this looks like. We looked at all of the test examples in the CFAR10 training set. And remember, we have a data model for each one. We then picked a bunch, I think about 100 random subsets of the CFAR training set, trained models on them, and then looked at the output of these models on the target examples, on all of the target examples. So on the x-axis, we're going to plot the data model predictions for what should happen for each of these cases. So each, it's going to be a scatter plot. Each dot in the graph corresponds to a specific target example with its own data model and a random subset. The x location of each dot is going to be what the data model predicted the margin should be. And we can calculate this obviously just by feeding the characteristic vector of the subset, the indicator vector of the subset through the data model. And on the y-axis, we're going to put the actual expected margin. And the way we evaluate this is just by training 100 models on the same subset Si and computing the average margin. And the result is that data models are actually able to predict the result of network training, sort of, at least for us, surprisingly well. So the large blue line in the middle is aggregating over target examples and random subsets. I've zoomed in on like a little part of the graph here where we look at, like we color each individual target example separately. So that it's clear the correlation holds even conditioned on a specific target example. But what this shows is that essentially given a random subset of the CFAR10 training set and a given target example, I can predict without training a model what the margin is going to be, what the margin of a classifier trained on that subset is going to be on that target example.
Question here, when you train these new models, these are also ResNet 9s that you're training?
Yeah. In our paper, we actually have what we call like a data model transfer experiment where we predict the margin of a ResNet 18 using the data models constructed for a ResNet 9. And we find that you can actually predict them pretty well, though not 100%, obviously, because it's through the lens of the architecture.
Okay, thanks.
But yeah, this is like the same training setup. The only thing that are different is that they're new random subsets. They're not the same ones you use to construct the data model. Cool. Yeah, so the conclusion of this is that at least for these random, like 20% of the training set subsets, data models can actually successfully predict the result of end-to-end training. So we've managed to sort of wrap up all the complexity of SGD on like cross-entropy loss and all this stuff, and model it just as a simple linear function of which training examples we trained on. Okay, so we've gone through predicting data, constructing data models, and then evaluating data models. The last part of the presentation, I want to go through how we actually apply these beyond just saying like, wow, it turns out we can model training with a linear function. It turns out they actually have a lot of cool practical applications too that we're pretty excited about. So the central sort of theme of all of these applications is we're going to take a place where we're going to take an application where evaluating a lot of models would be really useful, but probably too expensive. And then replace the model evaluation step with a data model to enable the application. And what we find is that data modeling is actually a surprisingly versatile framework for analyzing model predictions in a bunch of settings. So we have a lot of applications in our paper. I had to pick a couple to put in these slides. The ones that I'm going to talk about are analyzing what we call model brittleness in data space, predicting data counterfactuals. I'm going to skip over a couple, and then I'm also going to talk about using data models as a way of embedding images into Euclidean space. Okay. So we'll start with what we call analyzing model brittleness. And we're going to define brittleness of a given prediction as the smallest set of training examples necessary to flip, sorry, it says learn, it should say flip a prediction for a target example X. So if I have, for example, like a model that I've trained that gets a certain dog correct, but I tell you, like, actually, if you had removed these 5 images from your training set, the dog would have been classified as a car, we would call that a brittle prediction because it hinged on so few images from the training set itself. So this is like a visual demonstration of that. And the sort of naive way to figure out how brittle all of my predictions are would be to just try training on every possible subset in increasing order of the training set, in increasing order of size, and just see which subsets flip the model prediction. So I could take this plane, I could take the CFAR10 training set, and I could try removing each one example individually, seeing if that flipped anything, and then removing every pair. The problem, obviously, is that this doesn't scale in any direction. Like, you'd have to try exponentially many subsets of the training set. But again, recall that the sort of the theme of all of our data model applications is, instead of doing this brute force search where we try every single possible subset, what if we instead use, like, for any given subset, I can use a data model to predict what the model, like what the output of the model is going to be if I were to remove that subset. So like for this example, for this counterfactual training set example in the middle of the slide, I could construct the indicator vector of that subset, I could feed it in my data model, and I could get an approximate answer for what I think will happen when I train the model and evaluate on this plane. And I can use these predictions to actually perform a guided search instead of a brute force search. And so this guided search allows us to reduce training on exponentially many subsets to training on just a few subsets that the data model has identified as like as plausibly flipping the prediction. And by doing this, we're able to get a sense of, for every single example in the CFAR10 training set, we're able to get sort of a lower bound on an upper bound on how brittle it is. So we're able to find pretty small sets of training examples for each test example that would flip the prediction of that test example. So the graph I've shown here is a cumulative distribution function. And so just to interpret a single point on this graph, what it tells us is that for 25% of the examples in the CFAR10 training set, removing 0.2% of the training set specific to that target example suffices to actually flip the prediction on that target example. And I mean, you can read more points off the graph. I think for 50% of examples, all it takes is 0.4% of the training set, or 250 images. And so by leveraging data models as a way to predict model outputs, we're able to very quickly identify these subsets that we then use to put a bound on model brittleness.
And this is like 250 images, but each image is different depending on the test image, right?
Exactly, yeah.
So it's not like there's like some magic set of 250 images in the CFAR10 training set that if you got rid of those, your model would be half as accurate. It's like...
Yeah, that's exactly. It's like for a given, like if I selected an example at random from the test set, then like with 50% probability, that example is flippable by removing 250 training examples.
Did you run this other analysis? Like I'm curious, is there a large subset of CIFAR10 that you could have that would give you a terrible model?
We have run some of these analyses. We're still working on it, and hopefully
Okay.
we'll have results for questions like that very soon.
Okay.
The short answer, I think, is that for CIFAR10 specifically, no, but for other data sets, that the answer is a little more interesting. Okay, cool.
So if you look at the very left end of this plot, I guess this is where things also get interesting for privacy, right? That this would seem to suggest that there's like, I guess this lets you identify maybe some memorized labels.
That's exactly right. Yeah. Yeah. So to the left of this plot, you can find like sort of a significant chunk of the test set that whose prediction would significantly change even if you remove like 10 training images or something.
And this is for complete label flips. Like, I guess, yeah, if you looked at just
so actually
something
really
like
interesting thing, that I thought was going to animate onto my graph, but I didn't animate onto my graph, is that this is just for removing examples. Like, so you're not actually flipping the label of the training example. If I also let you flip the label of the training example, then the graph looks like sort of absurdly more, like models are absurdly more brittle. Like we're able to flip, like, I think the vast majority in like 30 by flipping 35 training labels. But this is just for removing the examples.
Right. Yeah, I meant the label flip on the target example.
Oh,
that
yeah,
basically, if you look at something slightly weaker, like maybe reducing the confidence from 90% to like 50% or something, then you would probably need even fewer examples.
Yeah. And we have some graphs in our paper of like how the number of examples removed correlates with like the average decrease in margin and sort of smoother metrics like that might make more sense.
Cool.
Great. Thank you for the question. Okay. Yeah, so these brittle predictions, or our algorithm for finding these brittle predictions, are kind of just a specific case of a broader setting that we call data counterfactuals. And broadly, sort of a data counterfactual just says, like, predicting a data counterfactual just means, can I predict the effect of removing a specific set of images from the training set? So the reason this is different from the evaluation scatter plot I showed earlier is because now we're no longer thinking about, can I predict model outputs on random subsets of the training set? Instead, I have very specific images that I'd like to remove. And I would like to see if my data model can still predict the effect of removing these specific images on model output. So in sort of the supervised learning framework that we were thinking about earlier, this would be sort of like out of distribution prediction for data models, where the subsets themselves are out of distribution because they're not random 20% subsets of the training set anymore. Nevertheless, we find that even though they're not trained on these data counterfactuals at all, what we did in this graph is consider a bunch of sort of standard ways of removing images. So we looked at, for a given target example, we looked at removing the most influential images based on influence functions. We looked at removing the most similar examples in representation space, in like a fixed model's representation space to a given test image. Basically, we looked across a bunch of heuristics of how do we remove the k most similar training examples to a given test example for varying values of k. So each dot in this graph corresponds to what we call the data counterfactual in the last slide, removing a very specific targeted portion of the training set and seeing whether a data model can still predict the outcome of training without that very specifically selected subset. And it turns out that for a lot of these natural removal methods, you can actually predict the result of training surprisingly well. And one thing we wanted to highlight is that there's sort of this like, so each color here in this graph represents a different heuristic for how to remove the images. So across all heuristics, the correlation between the predicted model output and the true model output is really high. But for a specific heuristic, it's even higher. So there's sort of this clustering happening where like each heuristic has its own, sort of has its own slope in this graph. And we haven't really looked into why that is, but we thought it was an interesting phenomenon. And so, yeah, as I mentioned before, even though the subsets that we're evaluating on here are out of distribution, because instead of being random 20% subsets of the training set, they're now the whole training set minus a specifically chosen target set. Despite them being out of distribution, we can still very accurately predict the result of removing them from the training set. Okay, the very last example, the very last application I want to highlight before getting questions is using data models as a example embedding. And what I mean by this is this sort of a little specific to linear data models. For linear data models, which is the one we consider, we predicted model outputs as a linear function of this characteristic vector that was parameterized by this weight vector, theta x, from all the way from the beginning of this presentation. Instead of looking at theta x as the parameter of a linear predictor, though, we can actually look at theta x as an embedding of a given target example into R 50,000, where 50,000 is the size of the training set. So specifically, recall that we fit data models with L1 regression. So what we have is sort of this really nice sparse embedding where each coordinate of the embedding corresponds to one coordinate of the weight, which corresponds to the predictiveness of one training example in the training set. So what we can think of this as is a vector in R 50,000, where each coordinate of the vector tells us how predictive the corresponding training example is from the original CFAR10 training set of model outputs on this test example. And it turns out that this embedding, in addition to having nice, well-defined coordinates, where each coordinate just corresponds to a given test example, training example, also turn out to have really nice and useful structure.
So the way I should be reading this, oh, okay, maybe you're about to say that.
Okay. Go ahead.
I was going to ask, the way I should be reading this like green-red thing is that this airplane is like, because this training airplane on the left is present, that's good, but if this frog, which is the same color, is present, that's bad, because it will push it in the wrong direction. And this other airplane is good if it's present, and this other deer is bad if it's present.
Exactly, yeah. And like that good or bad is determined by the sign of the weight vector.
Yeah.
Because the weight vector is going to like be multiplied by this 1, 0 presence vector. So that's it. That's exactly the right way to read it. And so, yeah, as Nicholas pointed out, this basically gives you a feature vector for a given target example. It gives you a feature vector where each coordinate in the vector says, like, is this training example good or bad for me? With a scalar value as well, obviously. Okay, so one manifestation of this useful structure that I was talking about is that we can now define a natural similarity metric even between two test images. So if we have two different test images, each one has their own data model, we can use the data model to get a embedding for each test image, where the embedding sort of represents how the training set causes the model class to predict what it did on the given test example. We can compare two data model embeddings from two different test examples to get a sense of whether these test examples are acted upon similarly or differently by the model class. So if two examples, X1 and X2, are really similar, then I expect them to sort of be acted upon in similar ways by the training set. And so they should also have similar data model embeddings. And so by looking at the inner product between pairs of data model embeddings, I can get sort of a really nice natural similarity metric between images. And going even further, we can take this similarity metric. We can take an entire test set of images with, again, their corresponding like 10,000 data models, and we can compute a full adjacency matrix for an image data set. So I have a highly editorialized version of this adjacency matrix here, but you can think of the green edges as things whose data model, as images whose data model embeddings are very aligned, and the red edges as test images whose data model embeddings are not aligned. And we can use this adjacency matrix, we can use the similarity metrics to basically construct a graph over our entire test set where similar images are close together and very dissimilar or sort of images that point in opposite ways of each other, like the red deer versus the red plane, are far apart in this graph. And even though we didn't get to explore it very much in the paper, we're really excited about the opportunity to basically apply a bunch of standard graph algorithms that have been studied for ages to like the CIFAR10 test set. So we did two really simple things based on this graph that I will that I'll briefly talk about. But in general, the possibilities here we think go far beyond what I'm about to show. So the first thing we thought is like, okay, we have a graph. What do people usually do with graphs? Clustering is sort of the very first thing that pops out at you. And so applying spectral clustering, which is just any clustering algorithm, to this data model embedding induced similarity graph, we get a lot of really natural looking, really, I guess, qualitatively high quality image clusterings that we weren't able to find with other methods. So I've shown two example classes here. The rest of them are in our paper, but this is sort of a very self-explanatory application. We were able to cluster the CIFAR10 test set just using these data model embeddings.
So is this clusters of boats, or did you cluster them and it only found boats?
These are clusters of boats.
Okay.
Yeah. So we like looked at each class, and then we looked at the subgraph corresponding to that class, and then we applied clustering within that subgraph.
Okay.
Going even further than this, we can also apply SVD to this adjacency matrix and uncover these sort of directions in data model space that correspond to features in image space, or things that look like features, at least in image space. So here I've visualized the top three principal components, or SVD components, from this adjacency matrix. And you can see that test images who have very high correlation with this direction tend to have one feature, and test images that have very high negative correlation with this direction tend to have either a different feature or the same feature in an opposite direction. So here, like the top principal component identified red cars and white cars, and then the corresponding things that had negative projection on that were white trucks and red trucks. Similarly, in the second row, you get like blue background planes dragging you in one direction and blue background birds getting dragged in the other direction. And so in our paper, we sort of studied these a lot more. And we also show that they're sort of causally grounded in how the model actually makes predictions, in the sense of you can remove there's a really natural way to remove the training images that correspond to a given principal component. And removing that principal component tends to very negatively affect all of the test images along that principal component without affecting much else about the data set. So it sort of behaves exactly how you would want, like, I don't know, like qualitatively PCA to work on image data. So that's all the.
You study it's sorry. So you study it's quantitative similar to PCA, but what's the difference?
Oh, sorry. I just mean like if I were designing PCA to work semantically on image data sets in terms of like some nice notion of feature, this is how you would want it to work. But what we actually do is just apply PCA to the data model embeddings rather than to the images.
Right. I mean, of course, from those images, looks like if we just apply PCA to the image itself, or maybe to some kind of, embeddings, right? Final layer or, neural, whatever, the tangent kernel, all this stuff. Wouldn't you get the similar results? I try to understand what's the difference between your approach.
Yeah, that's a great question. Mm-hmm. So in our paper, we do a much more thorough, basically a comparison with doing PCA on the last layer representations from a neural network. Mm-hmm. And we find a couple of sort of very key differences. So one thing is that if you look at the last layer of a neural network, essentially all of the variance in PCA is captured within like the first 12 directions of the embedding. So if you visualize beyond the 12th direction, or sorry, the first 10 directions. So if you look beyond, like if you look at the 11th direction of the embedding, you end up with images that look extremely dissimilar to each other. Whereas if you look at the effective embedding, the effective dimension of data model embeddings, it's much, much higher. There's like 300 or 400 directions that each seem to correspond to some human meaningful feature. So that I say would be the first difference. The second difference, which might be getting into the weeds a little bit, is that when you do PCA on representation space, the actual representations, the actual principal components that you get are just sort of like abstract vectors. And the only thing you can really do is like you can only compare them to the fixed model that you used to compute the embeddings. Whereas here, each coordinate actually has an interpretation as a training, like as an image from the training set. So we can actually take a principal component and then say like, what are the most important training images for this principal component?
Right. I think the output, like a layer, they are influenced by your training task, right? If your training task is just some binary classification, it wouldn't care all these details. It's probably more useful to look at the input embeddings after the, kind of the first layer, or maybe after the convolution layer, and looking maybe at the similarities, right, between like images. I just curious. By the way, I think this is very interesting work. I'm just curious about how your method compared to the more kind of content-based kind of methods.
Yeah,
right?
Yeah, it's a great question, and I may not have done it justice here, but there's a entire section. There's like a good half page in the paper that compares to representation embeddings.
Sure.
That I can.
Okay. I'll probably read the paper. Thanks.
So in the first part of the response, you said that like there are like 10 dimensions first final layer and like 300 triggers. By this, do you mean like it explains variance? Like exactly. You do PCA and you say like this many dimensions, you need to explain like 90% of the variance?
Exactly. Yeah.
Okay. So that's a lot of dimensions to explain that variance. That's very nice.
It's perhaps more about how wide it can. I mean, if you take a trained model, then it's more about, I guess, the final layer. How many directions are there? Probably reflect your training, the complexity of a training task, right? So, right.
You're related to this. Do you know how these numbers look like if you take the representation layer of like a very complicated model, like say CLIP, which we know gives you like very, very rich features?
That's a great question. No, we can look into that. We haven't.
So here you looked at the representation layer of a CIFAR10 model to compare.
Yeah, of the same kind of model that we, like of the same architecture that we use to actually compute the data models.
Mm-hmm. Because I guess a lot of these, essentially this entire kind of graph theoretic approach here, you could even imagine, what this would look like by doing this, say, just with clip embeddings, which, I mean, you could debate which one is kind of more expensive to compute, and that not everyone can train clip, presumably. But since it already exists, you might be able to do some of these analysis with these kind of generic embeddings as well.
Yeah, that's a great point. One thing I do want to point out about that we I guess we thought was a point in favor of these sort of data model embeddings is that it becomes very obvious if I train two neural networks, even of like even of the same architecture, it's not really clear how to combine data from the two neural networks. There's like a lot of work on representation alignment and figuring out what each neuron means and mapping it to a neuron in the other network. Whereas here you have sort of a grounded, like the representation is grounded in the sense that each coordinate corresponds to a training image. So even if I have like a bunch of data from ResNet 9s and a bunch of data from ResNet 18s, and I want to compare the representations, I can actually compare them like point-wise. Like I can compare the ith coordinate of this representation versus the ith coordinate of that representation. And the result is something.
So do you think that by doing exactly this, by sort of taking the data model you get from say a ResNet 50 and another one you get from a ResNet 9, that by comparing these, you might get some insights into sort of why ResNet 50 works better than ResNet 9, or sort of what exactly it's learning that ResNet 9 isn't learning?
Exactly.
Mm-hmm.
Yeah. Oh, yeah, my next slide is actually the takeaway slide. So if anyone else has any questions, I'm happy to answer them now. Cool. So I guess in summary, what I introduced during this talk is the data modeling framework, which is a new framework that we hope will help shed some light on how exactly training data and learning algorithms combine to yield model predictions. The, I guess, key feature of this framework is to learn a map directly from the training data to model outputs using the supervised learning framework. We considered a really simple linear instantiation of the framework where the inputs are just binary vectors about the presence of each data point. And it seems like these linear instantiations actually worked really well. And then we explored a couple of tools for model and data understanding based on the resulting data models. The paper, as I mentioned a couple of times, has a bunch more experiments, including on another data set. And we also have a blog post either up or coming soon about data models. And we're happy to answer any questions online or offline. Thanks so much.
Thanks for the great talk. Yeah, I'm curious Florian's question of what happens if you compare the differences between one architecture and another, and if this could explain why some kinds of models are able to make better predictions than others. Like, is it the case that, so okay, here's a hypothesis, I have no idea if it's true. A ResNet 50 can learn more from a smaller amount of data than the same ResNet 18.
Yeah.
This seems like something you could answer, right? Like you could say that take the data model from the ResNet 18, take the data model from the ResNet 50, and ask like how many examples did you need for the ResNet 18 to get it right versus for the ResNet 50 to get it right, and say like, yeah.
That's exactly it. Yeah, yeah. So you could look at like how well supported basically each prediction is for the ResNet 18 versus the ResNet 50, and you could test the hypothesis for, like, you could hypothesize that the reason ResNet 50 does better is because it's getting all of these test examples who only have like 5 corresponding training examples in the training set, and like a ResNet 18 isn't able to pick up on these at all, but a ResNet 50 is, and then that could manifest as like in the brittleness experiment, for example, you might see like a much earlier spike for ResNet 50 that corresponds to all of these examples that you learned based on very few training inputs.
And this would be bad in some sense, right? Like it would mean that the more accurate models are more accurate, but they're more brittle. That's why they're more accurate.
That would be interesting.
Yeah.
Did you look at all whether these sort of how these data models behave for points that are kind of very far out of distribution, and whether you sort of still get you can still predict things very nicely there? Like say you'd want to create a data model not for like a CIFAR-10 training or test point, but for like an adversarial example or for a very corrupted point from CIFAR-10.
Yeah, we've been looking into that a lot actually, and we have some results, but none I have enough confidence in to show. But
Okay.
but yeah, exactly those kinds of questions we're looking into, and we hope people will look into, I guess, as follow up.
And also a dumb experiment. But I wonder what would happen if you trained on like random labels. So like do the rethinking generalization thing.
Mm-hmm.
And I have no idea why this idea occurred to me. I don't know what this would do, but I'm curious, like if you trained on completely random labels, like we know models can fit them.
Yeah. You're curious if there's like a structure to the test predictions, even though you trained on random labels.
Yeah, like the way that the model happens, when a model fits random labels, is it the case that it just like, random hash function and just memorizes the outputs? Or does it like find some correlations between inputs that happened to just by chance these 3 airplanes were labeled as dog, and so I could just like more easily get the answer right by remembering these 3 airplanes are dog? Or you could imagine that it just like independently everyone is just memorized separately. Yeah,
that's a fantastic question.
Yeah, I don't know. I don't know what we're to do, and I don't know why. Like, odds are if you do this, you get nothing interesting. But might be interesting to see.
I guess this, if you look at this, all this kind of neurotangent kernel, all this stuff, right? Which you actually look at the input embeddings. There, you don't care about the classification tasks. You're just looking at this image passing through some kernel, right? I think that probably will give you more kind of, the task independent kind of similarity there, right? Be interesting to see the difference, right?
Yeah.
So another random question is, what if instead of looking at adding or removing examples, you corrupt the labels and see if, corrupting the label of this one results in bring up the label of the prediction somewhere else?
Yeah, let me check if I have some extra slides, but I'm not actually sure that I even got those into the extra slides. Give me 1 second, actually, because I think I might be able to find.
Thomas, were you imagining training instead of on training on random subsets? Training where you corrupt random subsets?
Yeah.
Oh, okay.
Yeah, so it's slightly different than what you're thinking of.
Yeah. No, we hadn't thought of that, but that's really interesting. One thing we had thought of is like looking at weightings of the training data instead of like having just binary leave it in or out. But we decided that we didn't understand how well training data, like we didn't understand how training data worked, like weighting worked enough to do it. But that like relabeling the examples would also be really interesting.
I guess the difference you could hope to observe would be, as opposed to just removing it, there might be some examples where if you mislabel, they just really had an outsized impact if mislabeled. but just
Yeah.
removed, it's sort of not so bad.
Yeah.
And so
Yeah,
it might be
and I think-
qualitatively different.
Yeah, like in general, I think removing and relabeling, at least for like our brittleness experiments, they tend to do like very qualitatively different things, because for removing, like basically having duplicate training images doesn't hurt you for removing. Whereas for mislabeling, it hurts you a lot. Like if you have a test example that has a exact duplicate in the training set, but is also classified, but also has like a bunch of kind of similar training examples, then if you remove the duplicate from the training set, nothing happens. You still get it right. But flipping the duplicate like basically kills your accuracy. And so you get these like you get these like kind of qualitatively different relations going on.
This would be a little bit cheating, but could you find, presumably you could find a subset of CIFAR10 training examples, which if removed would give you a higher test accuracy. Most likely those would be like, I don't know, like mislabeled training examples or something.
Yeah.
Well, it would be quite fun if you could show that, I don't know, there's like 1,000 examples in your training set that if you just removed them and didn't train on them, you would actually get like 97 instead of 95% accuracy.
That is really cool. Yeah, we hadn't thought of that.
There's a paper that actually does this. It does it with worse techniques than yours because, of course, they didn't have this. Let me try and find it. It's called like dataset dropout or something.
Huh. Yeah. Yeah.
I guess you'd have to be careful, yeah, that because you're kind of looking at the test set a lot when computing these things. You could be overfitting in some sense, but yeah.
But, yeah, I mean, it'd be really interesting. And I think you could, like, if it worked, you could try to take it a step further too by like basically doing all the data model stuff on a validation set and then getting rid of the training examples that you predict will have a very bad impact on the validation set, and then seeing if removing those training examples does like also helps you on the test set that you never looked at.
Yeah, exactly. I was going to suggest just splitting your test set in half and like doing it half and half. Yeah.
All great experiments.
I can't find the thing. I've certainly seen a paper that Florian ran exactly your experiment and showed that there exists a way to train on CIFAR10 with less data to get a more accurate model. I can't find it right now, but it sort of did this kind of thing. But it would, even if cheating, I would be okay with this using this data models thing, right? It would be fun to find a subset of CIFAR10 that you could say like, here is the best CIFAR10 training subset to use to get the best test accuracy.
Yeah.
Okay.
Is there hope that you could train these data models in situations where you can't train like 100 times as many models as there are training data points?
Yeah, we're looking into it. So actually, the nice thing about the regularization, like the sort of L1 objective we have set up, is that you get like it's not that bad if you halved the number of models or something. But if you have like 10x or 100x fewer models, you're not going to do so good. We are looking into like more intricate ways of, because this is like the dumbest supervised learning problem you could set up, I guess. You just like kind of just train a bunch of models and then train on the binary vectors. We are looking into a couple of ways of making it more efficient, but nothing huge yet.
Cool.
Sorry. Thank you very much for coming to give the talk.
Well, thank you for inviting me.